you see, the first thing you see when you're not done the first thing you see when you look at this picture, you realize that this has more area above this line than here. See? So if this was a solid rectangle, then the centroid would be here. So the first thing you realize, this is not the centroid, this point. So this is not the answer. So let's just eliminate it. So that's not my centroid. Okay? Let's say no. No. Alright? What can I say? This geometry is very complicated. I cannot do any integration, and I cannot do any like summation of xi ai over summation of ai x bar. In fact, I can divide this into a small part of area like that. You see, later on you will have course in numerical methods. You can divide this into simple shapes like that, and then use this formula. But look, what happens if for this geometry you need a lot of little cubes, right? A lot of little cubes to get the accurate estimation of centroid. So what I'm trying to say, there is, for this question, for the limited time we had, you shouldn't do any calculation. But if I see you doing some integration, that something is wrong. You can't do that. Geometry is complicated. So I should use the rules of symmetry and some engineering intuition in order to find the centroid. So the first intuition is this is not the centroid because I have more area here. The distribution is not symmetric, so this is not the centroid, right? What else can I remove from these options?
The one that's not 400.
The one that are not 400. So you can see this is completely symmetrical about this line, right? So the centroid must be somewhere on this line and not this point. So somewhere on this line, not this point. So anything that is not 400, let's get rid of it. This is 400, but look, this is not the centroid because this is centroid of the complete solid rectangle. So get rid of this. This is not 400. Get rid of it. Not 400. It's 400, not 400, not 400. So automatically, with two observations, you realize this is my only remaining answer. And if you had an option like none of above, you should also consider that. But look, that's all I have right now. And now I come and check it. Where is 400 and 250? The x is 400, so it's on this line. And the y is 250. So 250 is somewhere here. It's something like here. You see that? And it looks about right because it's a little bit up. The distribution is upward, right? So this is the first part. So the answer to the first part is option B, right? Now let's go to the second part. The second part, you have exactly the same options, right? But I said, now in this case, you put a formula. So this geometry has over like that, and this is also symmetric. Now, what happens to the centroid? It goes to the right or left? to the left, right? So that's going to move somewhere we don't know, somewhere here. It goes to the left. So what can I say? Again, not 400, not above 400. So it should be smaller than 400. Which one is smaller than 400? Either this one, not this one, not this one, or this one. Not this one, not this one. These are the only options that is smaller than 400.
And 400. You've
Huh?
got D up there.
No, it should be smaller than 400. Not 400, it's smaller than 400.
Oh, you put it, okay, never mind.
Yeah, not equal. It's smaller than, because it's 400 when you have complete, this is symmetric. This is completely filled. Then it's 400, right? Now, which one is it?
F.
It's F, because what? Because this is smaller than 300 too. It's up to 300, it's not below 300. So you get 250, 250. So the second option is F. You see? That's the method. You get the answer just by eliminating the one that are terribly wrong. The ones that are terribly wrong. I mean, I'm not saying this is accurate, exact solution. It's just roughly, it's better than the other ones. The other ones are just simply not acceptable. All right, now we go to the next part, which is simply taking a surface integral. I want to do it here. That's my geometry. A simple right triangle. Let's first solve part A. Part A is say put the coordinate system at the left bottom corner here. So that's your center 0, 0, your origin O, X, Y. And this is Y geometry. From here to here is B. From here to here is H. Right? Now I want to do IY. Now according to the formula I have there, IY is X integral. X squared dA. Don't forget this is square. When you have just X to first power, that's centroid computation. Moment of inertia is always even, X squared, right? Over the entire area. But it turns out that again, this is a calculus 2 problem. Take this integral over this triangle, and your coordinate system is given at this point. So what should I do? First of all, I should find something for dA. If I find something with dA, just plug it in and take the integral. In order to do that, I take an element like this. You can choose different types of element. You can take it like here. You see? You can take dx, dy, two-dimensional element. But what I do, because this kind of mimics my x2, I just take an element like this one, and this is, if this is x and y, from here to here is what?
X.
X. So this tiny thickness is dx, and the height of this is approximately this height. This is b. This is infinitesimal, but this one is significant. Y of x, right, is not h. H is only when x is 0, it's right here. But this can be anywhere here, so the y will change. This height will change. You see that? Now, I want to write the expression for dx, for dA. dA is equal to, let's approximate this with a rectangle. So, in fact, I have a rectangle like that. This side is dx, this side is yx. So what's the area of this? dA is equal to?
dxy.
Yeah. So am I ready to just plug it in and take integral? Not yet, because I don't have yx. So how can I find yx? Let's go.
The line.
Yeah, the line. No, I'm trying to ask the student on this side, because I know you guys always answer it. But how can I find yx?
The slope of the line.
It's not the slope, it's just the length from here to here.
I think dA is supposed to be y, then it's dx.
Yeah, dx. Yeah, this is dx. So now we're talking about y. How can I get this y? Let's put it this way. I have 2 points, P1 with coordinate x is equal to 0 and y is equal to h. And this is point 2, P2, x is equal to b, y is equal to 0. And there is a line. This is a line, right? There is a line connecting these 2 points. From here to here. Now, my question from you is, what's the equation of line passing through point 1 and point 2?
Y minus 1.
Hold on. Yeah. Okay. What's the equation of line passing through? How can I get the equation of line going through the 2 points?
Just the slope one.
Huh?
It's the slope one. Y2 minus Y1.
Yeah. You see it?
Subtract from the lines.
Yeah, there's slope formula. You see, everybody knows. We all know it, but the thing is, because we didn't know this may have application in engineering, we really didn't pay attention in high school or calculus, right? We just say, oh, this is just boring. But look, right now you realize, well, if I can do that, then this is an application. Then I can find moment of inertia. Later on, in the second course, you can design actual beam. You can go to the lab and test it and see what you get is exactly equal to what you get on the paper. And that's amazing. You realize, oh, finally, this stuff, this ridiculous stuff, they have application. Then you may go back and review it. That's what I'm trying to say. Okay, so the equation of line is y minus, so the equation of line between these 2 points. So y minus y1 is equal to y2 minus y1 divided by x2 minus x1 times, that's the slope. So this is the slope formula, times x1 is x1. So all I need, I just get this x1, y1, x2, y2, plug it here. So this is x1, this is y1, x2, y2, right? Just plug it in the formula. So you get y minus y1 h is equal to y2, 0, minus y1 h divided by x2 b minus 0 times x minus 0. Right? And then take y, this is in fact the same y here. You see that? Instead of yx, I'll just say y. Then solve for y. Y is equal to h minus h over b times x. Right? And then this is going to be y is equal to h times 1 minus x over b. The end result. So this is the end result, the final result. for y. Now you have yx, right? Put it here. dA is equal to h times 1 minus x over b. There is a dx already here, dx. So that's your dA formula. Now I ask you, am I ready to just plug it in here and take the integral? Huh?
You have to find the balance.
Yeah, that's right. You have to find the bounds of integral. So let's do that. Let's write it here. So you have integral. You already have x squared. Huh?
Won't it be from 0 to what, b?
Yeah.
Yeah.
We will reach that point. So if we put integral from x squared, then dA. dA is right here. h times 1 minus x over b dx. From x is equal to 0 to x is equal to
B.
b. Right? 0 to b. Clear? From 0 to b. So, I'm going to open out some space here. Then, the next thing you can do, you can take this h out of integral, it's constant, right? You can just put this guy here, and then you're ready to take the integral. So you have one h here times this x squared, which is x to the third power over 3 from 0 to b minus 1b over b times, you already have x cubed, then you go to force forward from 0 to b. The total thing is multiplied by h. Right? So let's simplify that. If you put the bounds, then you get b cubed over 3 minus, again, b cubed over 4. I just said this is at b minus this is at 0. This is at 0, it's just 0, right? And that's going to be h times 112 b cubed. So it's going to be 112 h times b cubed. That's what you get. So this is the answer to part 1. So this is your IY. I with respect to this y-axis. Right? IY with respect to this y-axis. Now, the second part is say, now consider the axis that goes through the centroid. So where is the centroid? This guy from here to here is 1/3 of B. It's not 1/3, it's 1/3 of whatever this base is, right? Now if you have an axis going through that point, let's call it by bar, right? The reason that we see bar there is nothing just weird, right? It just, we want to distinguish between the one that goes through the centroid and the one that we originally had at this corner, right? So this is y bar and this is y. Now I want to find moment of inertia with respect to y bar. Again, I have two options. The first option, I go to this integral again. But look, this integral, right now, if this is my 0, then I should go from negative b over 3 to positive 2 over 3 times b. And the equation of line also will slightly change because the coordinate system is shifted. So it's going to work out for us, but it's going to be a little bit elaborate, more involved, more computational intensive. The second option that we always want to use as an engineer is parallel axis theorem. So if I have IY, the first one, part A, IY is equal to 112 H times BQ. This is already I computed, right? So I can use Faraday's theorem to just avoid doing integration again, right? So here I just write this formula that I have right there. Iy bar plus A d squared. Now this one I already have it. 112 H B cubed. Area is, what's the area of triangle? The entire area? Half BH, right? And the distance is the distance between two axes that I shift. And what's the distance? 1/3 B. B is equal to 1/3 B. Just put it here. Then you get 112 H BQ is equal to Iy bar. That's what we're trying to get, right? Plus area times 1/3 of B and the second power, right? So in fact you get Iy bar, now solve for Iy bar, is equal to 112 H BQ minus 1, this is 918 B cubed times H, which is, you can say HB, HB. It's 1/36 HB cubed. So you see, we didn't do integration, we just used Faraday's theorem. So it's going to be 190. Now, as a homework, optional, you don't need to turn it in. Go home and use integration to find moment of inertia with respect to the centroid. And see if you get 1/36. This is 1/36. 36 divided by 12 is 3. 112. 36 divided by 2. Minus 2. So yeah, it's 1/36. So it's 1/36 HB cubed. 1/36 HB cubed. Iy bar. Also, this is in your appendix. Everything in the appendix is with respect to the centroid. You can double check it with the appendix. All right?